So, homework for chapter 25 is due today, 15th. Homework for chapter 26 will be due on the 27th. We will have a review for chapters 25, 26, and 27 on the 27th, and the exam is scheduled for the 29th. You need to take it early, you can. I'll sit down and make sure it's ready in advance. That's a Wednesday, the last week. Yeah, okay, that's not a problem. I'll make sure to get it ready like early next week, so. I got a bunch of exams I need to get ready, so we'll just sit down and do all of them. But yeah, that's the last week. That's what it's scheduled for. If you want to take it early, you can. Just give me a little bit of prior notice so I can get it ready. No. So, continuing chapter 27 about optical instruments. We have the compound microscope. Which in the simplest form has two converging lenses. One, the eyepiece is close to the eye, while the objective is close to the object. And the object is placed near the focal point of the objective, giving a magnification of di over do, which is roughly di over the focal length of the objective. So that's how they get that number for the objective. And then the image is formed at the focal point of the eyepiece, which produces an image at infinity, where n over the focal length of the eyepiece. So magnification of the eyepiece is n over the focal length of the eyepiece. So where n is the near point of the eye over the focal length of the eye. So this is sort of the setup. You have an eyepiece. You have an image being formed by the eyepiece at infinity. You have an image formed by the objective, which is then turned into the image for the eyepiece. And you have the object down here. So the objective creates an image, then that image is used as the object for the next lens. And the total magnification is the multiplication of those two, which is di times n, which is being your near point length over the focal length of the objective times the focal length of the eyepiece. And you find di by using the actual, this is the object, but it's also. So here, for example, in a biology class, a student with a near point distance n of 25 centimeters uses a microscope to view an amoeba. If the objective has a focal length of 1 centimeter, the eyepiece has a focal length of 2.5 centimeters, and the amoeba is 1.1 centimeters from the objective. What is the magnification produced by the microscope? So here you'll have to use the lens formula. So, the magnification of a microscope is going to be minus di over focal length of the eyepiece, focal length of the objective DI times the near point of the eye. But DI, we have to find the DI, 1 over DI plus 1 over DO equals 1 over the focal length. In this case, it would be of the objective. The magnification is magnification of objective times the magnification of the eyepiece. DI over the focal length of the objective and over the focal length of the eyepiece. So minus D over DI equals 1 over the focal length. So 1.1 centimeters and 1 centimeter to find DI. DI is going to be 1 over 0.019, this, which is about 11 centimeters. And the magnification is minus 11 centimeters times 25 centimeters over 1 centimeter times 2.5 centimeters, which comes to the magnification of the objective is 11, the magnification of the eyepiece is 10, the magnification is minus 110. Now, a telescope is similar to a microscope in that they have an objective in the eyepiece. However, the objects observed are essentially at infinity, so the light will be focused at the focal point of the objective. And the objects themselves are very large, but their annular size is very small due to their great distance. So here we have a very distant object. We have an image formed by the objective at basically its focal length. So the image formed by the objective is at the focal point of the eyepiece. And then the eyepiece is used to form an image in your eye. And the total magnification of the telescope is the product of the magnification of each lens. Which ends up being, which is theta prime over theta, which is the focal length of the objective over the focal length of the eyepiece. And the length of the telescope will be the focal length of the objective plus the focal length of the eyepiece. And telescopes using lenses are called refractors. And the first telescopes that were made were of this type. They were made by Dutch lens grinders for using this. You can also use mirrors for telescopes. That is what Isaac Newton did. He was the one who developed the first mirror-based telescope. So it's desirable that the objective of a telescope be as large as possible so that it may collect as much light as possible. Each doubling of the diameter of the objective gives you 4 times as much light. And very large lenses are difficult to work with. They're thick, they're heavy, they have to have 2 precision surfaces. They absorb more light the thicker they are. They're harder to hold because you can only hold them by the edge. Therefore, large telescopes these days are made as reflectors. The objective is a mirror rather than a lens. The mirror only has 1 surface. It can be made very thin. It reflects almost all the light that hits it. It can be supported from behind. It's also possible to fine-tune the mirror if it's thin, by bending it. So all large telescopes these days use a mirror. This is the original design of a reflection telescope, similar to the one that Newton designed, where there's a primary mirror, a secondary mirror to move it out the side to an eyepiece. Modern telescopes often have a secondary mirror that sends it out the back, a hole in the center in the back for detection. They also sometimes send it out the side. Well, sometimes they have it down and then there's a thing where it can go either out the back or out the side. In theory, you can have one where you even have a detector like up here. There's no secondary. That's what's used for radio telescopes a lot of the time. So two telescopes have identical eyepieces, but telescope A is twice as long as telescope B. So remember, for a telescope, the total magnification ends up equaling focal length of the objective over focal length of the eyepiece. And length is focal length of the objective plus focal length of the eyepiece. So if you have two telescopes with identical eyepieces, but telescope A is twice as long as telescope B, is the magnification of telescope A greater than the magnification of telescope B, less than the magnification of telescope B, or is there no way to tell? Actually, let me do something quick. I'm drawing on the screen. Should be animated. And it should be the wrong button, but it worked. So that ink should have shown up in the middle of the writing, but I've forgotten to animate it. So for this, magnification is focal length of the objective over focal length of the eyepiece. And length is focal length of the objective plus focal length of the eyepiece. But given in the problem, the two telescopes have identical eyepieces. So those two are fixed. So if we increase L, keeping F eyepiece the same, F objective has to also increase. That make sense? L equals F objective plus F eyepiece. If F eyepiece can't change and we increase L, we must be increasing F objective. So if F objective increases while F eyepiece stays the same, the magnification must increase. So the magnification will increase, MA is greater than MB. Basically, you got a better lens, but it has a longer focal length, and your eyepiece is similar. Here you can see the other issue is that to get very high magnification, you kind of need a very long path. Well, to get F objective better, you could shorten F eyepiece. So a telescope has a magnification of 40 and a length of 1,230 millimeters. What are the focal lengths of the objective and the eyepiece? So we could start by looking at magnification. Magnification is focal length of the objective over focal length of the eyepiece. This tells us also length is focal length of the objective plus the focal length of the eyepiece. This means we can combine these equations into one. We know the magnification is focal length of the objective over focal length of the eyepiece. So the focal length of the objective is going to be, and that's 40. So 40 times the focal length of the eyepiece equals the focal length of the objective. And we could substitute that into this equation. We get 1,230 millimeters equals focal length, 40 times the focal length of the eyepiece plus the focal length of the eyepiece, or 41 times the focal length of the eyepiece, which is 30 millimeters equals the focal length of the eyepiece. And the focal length of the objective is going to be 40 times 30 millimeters, or 1,200 millimeters, or 1.2 meters. So the focal length of the eyepiece is 30 millimeters. The focal length of the objective is 1,200 millimeters. Now, let's talk about lens aberrations. So spherical aberration occurs when the light striking the lens far away from the axis doesn't focus properly. And it can be fixed by grinding the lens to a precision non-spherical shape. This, however, is hard. Turns out grinding things into spheres is easy when it comes to grinding lenses, but non-spherical curves are hard. They're not impossible, they're just very difficult. It turns out that if you're doing a spherical shape, it's sort of self-correcting. Like if you do a sloppy grinding job, it tends towards a sphere. So it's easy to do spherical curves, but not non-spherical stuff. Additionally, there's something called chromatic aberration, where different colors of light focus at different points. And chromatic aberration can be improved by combining two or more lenses that tend to cancel out each other's aberrations. This will only work perfectly for a single wavelength, but it can work for a range of wavelengths. This is what's done with camera lenses. They work to cancel each other's aberrations out. So camera lenses are so complicated partially to get rid of chromatic aberration. They also do stuff with coatings and things. But yeah, that's part of the issue. And that is the end of chapter 27. So the human eye is focused by the ciliary muscles, which change the shape of the lens, while a camera, on the other hand, is focused by changing the distance from the lens to the film. The near point is the closest eye at which the eye can focus, typically around 25 centimeters. It varies from person to person, and it gets worse as you age. Hence, reading glasses. The far point is the furthest point at which the eye can focus, typically at infinity. The F number of the lens is the focal length divided by the diameter of the aperture. It gives an idea about how much light is passing through. In lens combinations, the image formed by one lens serves as the object for the next. Nearsightedness occurs when the image is focused in front of the retina, causing the far point to be closer than infinity. It can be corrected with a diverging lens. Farsightedness occurs when the image is focused behind the retina, causing the near point to be more than 25 centimeters from the eye. It can be corrected with a converging lens. The refractive power of a lens is measured in diopters when the focal length is meters, is 1 over the focal length. So diopters are inverse meters. A magnifying glass is a converging lens. Its magnification is given by if you have an image at infinity, the magnification is the near point divided by the focal length. If the image is at the near point, the magnification is 1 plus the near point over the focal length. You gain a magnification. A compound microscope uses two lenses, the objective and the eyepiece, to form an image of a small object placed close to the focal point of the objective. Its magnification is given by minus DIN over focal length of the objective over focal length of eyepiece. A refracting telescope also uses two lenses to form an image of a very distant object. Its magnification is given by magnification total equals focal length of the objective over focal length of eyepiece, and the length of the telescope will be focal length of objective plus focal length of eyepiece. And a telescope having a mirror instead of a lens of the objective is called a reflecting telescope. And all major scientific telescopes at this point are reflecting. Nobody really uses lenses anymore. And lens aberrations can distort images. You can also have aberrations with a mirror in a telescope. That was actually a problem with the Hubble Space Telescope. The mirror was ground slightly off, and there were issues with the focus of images because of it. And they had to send a mission up there to install corrective optics. And spherical aberration occurs because the off-axis rays do not focus at the focal point. It can be corrected by precision shaping the lens. So the perfect shape for a lens is not spherical. It's, I think, parabolic. But it's more complicated for lenses. For a mirror, it's parabolic. A similar aberration can occur in mirror. And chromatic aberration occurs because different frequencies of light have different indexes of refraction, and it can be corrected by using multiple lenses in an achromatic lens system. Also, there are other steps that can be taken. Yeah. And you can also choose your material to not have a lot of dispersion in the range you're interested in. You know what? That's a decent stopping point for today. We'll have next week for chapter 28, which probably won't take all of next week. And so for the lab time, I'm going to end the meeting. Since I can't figure out what I was meaning to do for the 10th lab, and everybody has missing labs, I was just going to do makeups today because everybody's here.